Hi everyone. So for my takeaway today, I'm going to be showcasing a personal project of mine where I used image classification and a fully managed deployment system to create something that allows me to easily train and deploy custom image classification models, specifically for the task of tracking basic habits. To start with, I'm going to give a bit more context around the project and basically just how it came to be. So back in university, I created a very basic website that allowed users to create and track habits. Overall, the system worked fine, but there was one major flaw, and that was that users had a tendency to lie. So there was no way to verify if these habits were actually being completed or not. And with this flaw at the back of my mind, it led me to ask the question, could you completely remove the user element from something like a habit tracking system by relying on something like image classification? This then led me to an initial experimentation phase where I trained several basic image classification models via a process of transfer learning for various habit-based binary classification tasks, such as is the desk clean or was the bed made? The resulting models worked surprisingly well, but the overall process was arduous. Every time I wanted to track something new, I would need to rerun the training scripts and manually get those resulting models to the device that was going to do the classification for me. So I decided I wanted to simplify this entire process to allow anyone to create, train, deploy, and monitor these custom image classifiers on numerous devices at once without needing to code or mess around with overly complex configuration. So in order to do this, I first needed some form of interface for the user to interact with. This handles the entire workflow from collecting the images for the model to deploying the actual models, and is where you create your classifier projects. For this interface, I went with a desktop app built using PySide 6, allowing me to easily leverage Python for all of the machine learning components. And talking about machine learning, at the heart of the app is obviously the model training system, which makes use of TensorFlow to train a model using a process called transfer learning, where you freeze a pre-trained base model and only train a small custom classification head that sits on top of it, meaning you only need 50 to 100 sample images of each state to get a very accurate model, leveraging the patterns already learned in the base model itself. So for this base model, I went with MobileNet v2, which was chosen specifically due to its architecture, which uses what is called depth-wise separable convolutions. So basically, in your standard convolution with, say, 3 input channels and 12 output channels, you would require 3 times 12 times the filter size computations, and each filter goes ahead and learns to detect specific visual patterns. So it goes and looks for your edges or textures and shapes by sliding across the entire image and combining all of that information from all the channels at once, where depth-wise basically breaks this process into 2 steps. So first, a depth-wise step. So you have 1 filter per input channel, allowing each filter to detect patterns within its specific channel. And then you have a pointwise convolution that basically combines these individual channel patterns to create your 12 feature maps representing the high level patterns. So this would reduce your computations from the filter size times 3 times 12 to your filter size times 3 plus 3 times 12. And you can kind of see that in the diagram here where it splits it out into the 2 split up processes. Then in the desktop app, we also enforce the conversion of the resulting TensorFlow model to a TensorFlow-like format. And this formatting includes 3 extra optimizations. So first is Operation Fusion, which is basically where, for example, a convolution followed by a batch normalization and ReLU activation function can be fused into a single TensorFlow-like operation, which reduces your memory transfers. Then second is a process called weight quantization, which reduces your 32-bit floating point numbers to 8-bit integers. And then finally is just an optimized execution plan that targets the specific hardware. Then just quickly from a usability perspective of the app, I made all the key training parameters easily accessible to users, so you can adjust things like your epochs, batch sizes, and learning rates. So over here in this demo video, you can see a user creating a project. So for example, a bed made tracker. They then go ahead and upload their positive and negative photos. So 100 of each of the bed in a made state and the bed in an unmade state. They can then go ahead and train the model. So here we just use the default parameters for the application. It will train that model. And then once this training is complete, we convert that model to a TensorFlow Lite format, and then we can verify that model locally by just feeding it two images, so positive for bed made and negative for bed not made. But obviously at this stage, everything is still done locally via the desktop app. So naturally, next we need some form of backend API that will act as like a communication hub between the client-facing desktop app and the live devices that are going to do the classification. So this is where we store our models uploaded from the desktop app, in addition to classification and status results sent back from those devices, and finally model assignments made by the users. This was all built with Flask, keeping to the Python theme, and makes use of Postgres to store metadata about the models, devices, and classification results, in addition to S3 buckets to store the actual models. So over here in this demo video, we can just see now that once we have that API up and running, we can go ahead and upload our model to the backend. That will upload it. We can then go ahead and see our new model, and we can just re-download that from the backend API. But again, obviously, a model living on the back end by itself isn't very useful without a device and some associated logic to make use of it. So we therefore have some code that runs on the devices themselves. So on first run of this code, it generates a unique device ID and registers with the API. It then periodically sends heartbeat requests to the API, telling it that the device is online while also receiving information about any new model assignments that should be downloaded. Then at regular intervals, it captures an image from the attached camera, runs inference using the TensorFlow Lite model downloaded, records the classification result with a confidence score, and sends this back to our API. So over here, you can just see an example of me running an installation script on the device itself. So this just completely automates your device setup. It will download the latest version of that device code, and then it will also create a systemd service definition that automatically starts the classifier on boot and will restart it if it crashes. Then after running the script, we have the device set up and we can place it in the right spot to take images. So in our example for whether or not a bed is made, I just went ahead and put it on top of my cupboard there with a view of the bed. So now moving back to the desktop app, we can see the live devices. We can then assign it our new model. So in this case, our bed made tracker. We can then go ahead and see all of the classification results come back, allowing us to basically view when the bed was considered to be in a made state or not. So you can see all those confidence scores there and the negative and positive results that come back. Basically, the beauty of this system is that once it's set up, it will just run autonomously. So the device sitting in my room will just continue to judge whether something has been completed with no opportunity for me to really game the system. It also means I have the flexibility to easily register new devices for other tasks. I can train it on anything else I want really, or I can swap out the models on existing devices without having to physically interact with those devices after the initial setup. So now that I sort of have an initial POC, I would like to look at maybe further improving those end devices to something even more user-friendly. So experimenting with something like a Pi Zero and a 3D printed case and battery. And then I would also like to look at improving the actual interface, along with expanding to more customizable options for the models deployed, such as like object detection and things like that. And then just, yeah, for those who want to check out the project in its current state, you can go check out this GitHub. And yeah, I think that's all. I hope you enjoyed learning about this project.